I'll do my introduction in two parts. So I'll start by introducing the Blackwell Seminar, and then I'll introduce our speaker. So the Blackwell Seminar was established in 2020, a year ago, to honor the contributions of David Blackwell to mathematical statistics, game theory, probability theory, and information theory. And David Blackwell had an extraordinary career and overcame numerous obstacles in the process. After receiving his PhD in mathematics at the age of 22, he spent a year at the Institute for Advanced Study in Princeton. In 1942, he then left Princeton and went on to teach at three historically Black colleges and universities, namely Southern University, Clark Atlanta University, and Howard University. And he stayed at Howard for 10 years, where he was quickly promoted to full professor and head of the Department of Mathematics. Professor Blackwell then moved to Berkeley, where he was recruited by Jerzy Neyman to become the first hire in the newly formed Department of Statistics. And there he became the first tenured Black professor in the UC system. During his nearly 35 years at Berkeley, he supervised over 50 doctoral students and served as both department chair and associate dean. He also broke racial barriers by becoming the first Black scholar to be appointed to the National Academy of Sciences. So the Blackwell Seminar is an annual seminar that focuses on topics at the interface between statistics and issues such as racial disparities, social justice, and ethics. And our speakers are invited to discuss their contributions to these areas. So I'll turn to our wonderful speaker. So I'm very pleased to introduce our Blackwell Seminar speaker this year, Dr. Kristian Lum. Kristian has had a varied and impressive career trajectory. So she's currently a senior staff machine learning researcher at Twitter. I just learned on the Meta team, apparently no relation to Facebook. And before that, she served as an assistant research professor in the Department of Computer and Information Science at UPenn. Prior to going to Penn, she served for 5 years as the lead statistician at the Human Rights Data Analysis Group, which really does some amazing work. If you ever get a chance to see them at a conference, give a talk, I would recommend it. I got to see Kristian give one a few years back. And sometime before that, she received a PhD in statistics from Duke University. Kristian is a founding member of the ACM Conference on Fairness, Accountability, and Transparency, and has served in various leadership roles since its inception. Her research examines the fairness and unfairness of predictive models, with a particular attention to those used in criminal justice settings. So Kristian, thank you for coming to speak to us today. We're so excited to hear about your research, and I'll hand it off to you now.
Great. Thank you so much for having me. And it was really wonderful to hear about the origins of this particular lecture. And I know everyone always says it's an honor to give a talk everywhere, but as I was saying in the meeting before this, it's particularly an honor to give a talk here in your department, and then even more so for this particular lecture. And I was going through the list of attendees. I saw some familiar faces, some familiar names, maybe some old friends. So hi to old friends, and hopefully some new friends there by the time this is over. So let me go ahead and share my screen. All right, I think I've done Zoom enough times to not have to check if it's working, but of course, if that's not, someone please speak up. So today I'm going to be talking about a forthcoming paper with my co-authors James Jandro and David Dunson called Closer Than They Appear, where I take a look at individual-level heterogeneity in criminal justice risk assessment. So this is definitely an applied talk. It's essentially applied Bayesian modeling, and I intend to make this really approachable for a wide variety of people from different backgrounds, though the statistical modeling is maybe a little bit interesting. And so if you don't know what I'm talking about individual level heterogeneity or criminal justice risk assessment, hang tight, because I do intend to motivate those and give you a sense of what I'm talking about before diving right in. All right, so risk assessment models are used across the criminal justice system to make contextually relevant predictions about future behavior of people. The context that I have thought about them most in is in the pretrial setting, which is essentially when someone has been arrested. Often what happens is they'll be taken to the jail, and a risk assessment instrument will be used to make a prediction about some potential outcomes. So some of those outcomes might be whether they will fail to appear, that's FTA. You'll see that acronym again going forward, whether they'll fail to appear if released, so fail to appear for future court appointments, whether they'll be rearrested, or whether they will be rearrested for a violent crime. And these predictions are usually made based on covariates such as the person's criminal history, their employment status, residential stability, past failures to appear, demographics, and sometimes interview questions. And these, the sort of which subset of those sorts of things in the set of X vary from tool to tool, but this is sort of just the cartoon version of what these sorts of things look like. So for statisticians, this setting probably looks fairly familiar. We could think of this as simply estimating the probability that Y equals 1, where it's 1, say, if the person does fail to appear or if they are rearrested, as a function of X, those covariates. In practice, often there are constraints put on what that function F can look like. In particular, often we like to have a linear function with integer weights so that a human can sort of calculate the function by hand. You don't need a calculator. All right. So then based on those predictions, so now we have these p hats, that's that probability Y equals 1, and maybe we'll get a distribution of those when we're building a model. So it'll end up looking something like this distribution here. It's really smooth in this case, would be maybe the distribution of our p hats, our estimates of the probability of that outcome, and that will be binned up. So the green region here will be all the people who are assigned to risk group 1, which will maybe be called low risk, yellow, which will be called maybe medium low, orange, maybe medium high, and red would be high risk. Now this classification to these groups, these bins, is then used to make recommendations about what should happen to that person before the conclusion of their case. So here's an example of one risk assessment tool that is, I think, probably one of the most popular ones used across the country. In this case, we have two site types of bins. So we have perhaps on the vertical axis, predictions of FTA, so binned up into groups 1, 2, 3, 4, 5, and 6. We have another prediction whether a person will be rearrested, that's NCA, and then you'd find your spot in there, and that'll correspond to that color. So the green here would be just let the person go. Red would be release not recommended, so don't let them go. And then orange and yellow would be different conditions with increasing levels of supervision. So I don't remember the exact details. Yellow might be they should go, but they have to call in, and maybe orange is something like they can go, but they need to check in with someone from pretrial services from time to time in person. I don't remember the details of those, but in any case, in increasing order of supervision, that's essentially how pretrial conditions are recommended in using these models. And it's worth noting that what the sort of outcome of this pretrial process, whether someone is allowed to go, whether bail is set, the conditions of them going, of them being able to be released, are really consequential on their lives. So for example, a lot of recent work has shown that if bail is set or if people are detained pre-trial, that can actually cause them to be more likely to be found guilty. The sort of mechanism being they're more likely to accept a plea deal that they wouldn't have accepted otherwise. All right. And so if you have been paying attention to a lot of the conversation about algorithmic fairness over the last, gosh, it's now 5 years, you've probably heard of risk assessments because these have become kind of the poster child of algorithmic fairness, or maybe better said, algorithmic unfairness. And I think this really began from this article released by ProPublica in 2016 called Machine Bias, where they said, you can read the subheading yourself right there. It says there's software used across the country to predict future criminals and it's biased against Blacks. And so the software in question in this case is a risk assessment model. And so much of the conversation in algorithmic fairness about these models has revolved around notions of group fairness. So this article showed that the false positive rate for white people was about 23.5%, as shown in that red box, and about 45% for African-American people in Broward County, Florida. And so based on these sort of group-wise differences, the sort of group-wise difference in the rate, in the false positive rates, they determined that the model was biased against Blacks. All right, and so this is one notion of algorithmic fairness that has been really popular in the literature, this sort of parity-based notion, this idea that whatever the predictive performance metric you choose for a particular model ought to be the same across different groups. So in this case, again, because the false positive rates differed across the different groups, they would say it does not meet a group fairness notion, a group fair notion of fairness. All right. What's been interesting is that in this literature of algorithmic fairness, we've also seen this, I wouldn't say competing, but maybe complementary or different idea about fairness called individual fairness, which is essentially that people who are similar should be treated similarly by the model. And this gets a little bit complicated to actually implement, but the idea here is that people who are similar with respect to their covariates should be treated similarly, where the magic in this, that's not just, okay, plug in whatever model, if their covariates are the same, they get the same prediction, which would pretty much be a property of most models you could think of, is that you need to define some sort of distance metric across those covariates that is sensitive to the actual context. And again, these sort of competing notions of fairness have really been at the forefront of algorithmic fairness research over the last, I'd say, 5 or 6 years. Now, these risk assessment models actually have been used for a long time, I think since at least the 70s. And what was interesting to me when I came to them is that there was this other sort of, I don't want to say battle, but this other debate about group versus individual notions of something within this literature that actually raged before the conversation in algorithmic fairness, but it was a little bit different. And this had to do with group versus individual probabilities, and in particular, how we quantify uncertainty about them. So if we think about this in the context of risk assessment models, in practice, people often look at things like group probabilities. So they'll take all the people who are classified to each of those groups. So these colors here correspond to the same groups I talked about before. So the green, low risk, yellow, medium low, orange, medium high, and red, high risk. And then look at the rate at which they experience that outcome that you're concerned about. In this talk, I'm going to be talking about FTA, so I'm going to sort of switch over to talking about FTA more specifically. So you could imagine they take all the people assigned to each group, look at the rate of failure to appear within each group, and then see that those rates are actually different between the groups. And when we talk about measuring uncertainty in these cases, it's actually pretty easy. It's sort of standard sorts of things. You can come up with confidence intervals around those group-wise rates. In this case, I'm showing 2 different confidence intervals, one black and one gray. The black one, of course, corresponding to one where you have much more data within each group. So in validation studies of these sorts of models, they often look to see that these confidence intervals don't overlap, to look for reassurance that these groups really are different. They're sort of statistically significantly different. And so when we start thinking about group probabilities, or what's being measured when we think about these group probabilities, we can see that this is just the average rate, or sort of the average. We're talking about a probability as the average rate within a group and our uncertainty about that average rate, right? And this might be something that's really useful to think about in this context. So from the perspective of a policy maker, you might think, if this risk assessment instrument, RAI, were the policy for release, what % of court appointments would be missed in aggregate? So that might be able to help you with planning. You also might want to know, how certain are we about that? You know, of course, modulo covariate drift or changes to the process going forward. You also might want to look at this and understand, on average, are the groups actually different? Now, what came up in this literature, so this was sort of the standard way of thinking about this for a long time, was this idea that although those group probabilities, or the sort of average within groups, do capture something about what's going on, they don't really capture something about individuals. So within each of those bins, you could have 2 scenarios, one here on the left, one here on the right. In the small variance case on the left, you would see that the probabilities of individuals in that group are tightly clustered around the group-wise average. So in these cases, each of those gray distributions correspond to a hypothetical distribution of probabilities within a group. On the right-hand side, we see that they're really dispersed around that mean, right? So in both cases, the average within each risk group is the same. So the average rate of failure to appear is the same within each group, but substantively, we're dealing with really different situations. So we might want to understand something about this. So from the perspective of a judge, we might want to know, how relevant is this risk label to the person standing in front of me about whom I have to make a decision? So this person has been, say, assigned a level 4 or a high risk designation. We know that on average, people within that group, say, have a 0.35 chance of failing to appear. On average, 35% of them do fail to appear. How relevant is that to this particular person standing in front of me? Now, for people who've been arrested and are being evaluated by one of these algorithms, they might also be more considerate about these individual relative to group notions of the group probabilities. So they might want to know something like, is this risk label likely to grossly mischaracterize me? Which would be something like that's happening on the right? So you're being told, or the model is saying, that you have a 35% chance of failing to appear, but maybe in fact you are very, very likely to appear. And so let's go through these scenarios really quickly. Scenario 1, in the small variance scenario, all individuals in group 4 have probability of roughly 0.35 of the outcome. And in this case, perhaps a judge might be comfortable detaining all people whose personal probability is 0.35 because everybody's right around that 0.35. They're saying, okay, this is a fairly good characterization of all the people in this group. So if the judge could know that the truth was scenario 1, perhaps they would be willing to make decisions based only on these group designations. In scenario 2, the large variance scenario, individuals in group 4 have probabilities that are widely varying, even though the marginal rate in that group is still the 0.35. And so perhaps in this case, having a 25% chance of detaining a person whose personal probability is less than 0.2 based upon this classification is completely unacceptable. So essentially what I'm saying here is some judge might also have a problem with saying, I'm going to detain all people who are in this high risk group because that gives me a 25% chance of detaining people who are very likely to appear. And so knowing which of these two scenarios we're in could be useful to people as they decide how they want to implement these tools or use these tools or incorporate them into their decision making in these, again, really consequential decision points in the criminal justice process. Unfortunately, if we have only one observation per individual, we can't really tell these two scenarios apart. So if we only observe each person once, what can we do? Well, we could fit a standard model and assume there's no individual level heterogeneity. So we could fit something like p hat I is, some function, maybe a linear function here of xi transpose beta hat. So essentially maybe a logistic regression or a probit regression, something like that. And then say, okay, that pi hat is actually this person's individual probability of the outcome. But you'll notice that for people who have the exact same covariates, where xi equals xj, for example, then they have the exact same probabilities. So making this assumption is in some way, I think, unsatisfying as a notion of individual probability, as there's not really any component of this model that is specific to the individual in question. And when you look at this data, there aren't that many covariates. They don't take very many levels. Even just sort of running this through a kind of, gut check, you'll find something like in the data set I'm talking about in a few minutes, something like 30,000 people share the exact same xi, so the exact same covariate vector. It's hard to believe that they all really have the same likelihood of failing to appear in this case. Again, if we only observe one per each person once, we could assume the empirical group-wise rates are approximately accurate representation of each person's individual probability. So that is to say, PG here is the estimated rate within each of those risk groups. So just going to assert essentially that PI, that's individual I's probability, is about equal to PG, basically assuming that we're in the small variance scenario for all I within G. And just sort of go from there. And that was roughly where this debate landed several years ago, was that, well, we can't really know without more than one observation per person. We can do some reasonable things like calibration checks to make sure that the estimated probabilities within each group roughly correspond to the actual rate at which people are failing to appear within those bins. Maybe we can do a finer binning to see that this all makes sense. And we should just from there kind of assume that these are right. And that was kind of where this ended. There was this long back and forth, with some I would say maybe ill-formulated statistical arguments on both sides of the debate about whether we should be using these group-wise rates as descriptions of individuals. And that's sort of where it stood for a long time. But then we come to modern day where we have access to a lot more data. In the past, these sorts of tools are built on a lot less data. And now not often, now for the first time that I've seen, we do have multiple observations per person. So what can we do in that case? So here's a really simple idea. Let me throw this out. If we have Yij is the outcome for the ith person on occasion j, so we're going to observe person I ni times, we could just have a very simple model where those Yijs are Bernoulli pi, so each person has their own individual probability p sub I, and just make an estimate using only their data. I think a pro of this sort of approach would be that it takes seriously the idea that before the law, you're judged only on what you've done, not what anyone else has done, right? So there's not anyone else's data that's going into building a model, to estimating covariates, to estimating weights, depending on how you're building your model. It's just you and your data, and that's the only thing that has any input into what we think you'll do in the future. Of course, one of the cons in this case is this would require many observations per person before you can estimate the probability with any reasonable degree of certainty, really at all. We could, of course, be Bayesian about it. And in fact, that's what we're going to do. So here I'm going to kind of build up to the model that we land on in the future. So here we could say those Yij's, the outcome for the ith person on the jth occasion is Bernoulli phi of theta sub I. So I'm introducing some new notation here. That phi of theta sub I would be equivalent to the p sub I from before. And then those theta sub i's come from some prior distribution that is indexed by eta. So in this case, this could be appealing because it offers this sort of coherent Bayesian framework for interpreting distributions over P as beliefs, and we get some regularization via the prior that can give us more reasonable estimates. So for example, if we're using only one person's data here and they don't fail to appear twice, they have 2 zeros, we probably don't think their likelihood is really 0, but that's what you'd get as a point estimate. In this case, we can sort of use that prior to give us more reasonable estimates. Of course, one con is that this approach is very sensitive to the prior, making it hard to justify as more objective. And one of the biggest selling points of using RAIs in the first place is that these are more objective ways of making decisions in this context. So maybe that's not great. Yeah, and so these are 2 different priors and they give you essentially 2 different answers. Now, if we have these multiple observations per person, we have enough of them, we can actually learn that prior. So we can essentially start making a hierarchical model. So again, now we have these outcomes, Yij, we have them Bernoulli theta, phi of theta I, that's the p sub I right there. And then we can learn this distribution, f of theta indexed by eta, where we're going to learn this parameter eta based on all the other people's data. Again, this is another Bayesian framework, and it's a nice compromise because the data informs you about how much other people's information should influence estimates of PI. So if we learn, for example, that the prior distribution or sort of the population level distribution is really dispersed, then we don't end up shrinking as much towards the sort of mean. We let the individual's data really inform about them. However, if what we learn is that across the population, everybody's probabilities p sub I are really tightly clustered, that even if we get somebody, for example, who doesn't fail to appear, maybe does fail to appear, say 2-3 times in a row, that's kind of accounted for because we know that's outside of the sort of range that we would expect based on the population. Of course, one con here is that we have to specify a class of distributions, f eta. And so now that this is basically where we landed, I'm going to sort of build up to the final model, which is the following, and this should look really familiar to what we have here. So we're essentially just adding in covariates. So now we have those individual outcomes, Yij, and we're going to model them as a linear function of the covariates Xij, recalling that those are things like criminal history, past failures to appear, some demographics like age, and this theta I component that we've seen before, which is that individual specific parameter, which represents their sort of individual or like inherent shift from what we'd expect based on their covariates alone. So this type of model, in my opinion, takes seriously the idea that individuals aren't solely the sum or the weighted sum maybe of their covariates. There's something different about them that we're not capturing, and we can only capture by giving them their own parameters. And of course, we still have these random effects distributions, f sub eta. We need a prior distribution on those regression coefficients. And this is really a fully specified Bayesian model. So pros here, we do have that individual specific parameter. We're also taking into account perhaps context. Often these Xijs will have things like residential stability or residential situation, for example. And we still have this nice compromise where the data informs you via learning this f sub eta about how much other people's information should influence our estimates of Pij. Cons are that it requires assumptions about f sub eta. And in this particular iteration of it, the individual effects do not vary over time. So we don't have, say, a beta j or even a beta I, for example. We just have a fixed beta across all individuals. So we made this really simple model here for really one big reason. And I think if you were to look at this model and delete out that theta sub I, this would look almost identical to most of the other ways that people are modeling this data and using it in the real world. And so the reason we didn't really do a whole lot of other, adding in a whole lot of other complexity here, like maybe time varying beta i's or something like that, is that we really wanted to make the minimal change to do something to account for individual level variability and see what happens, right? We want to sort of hew as closely as we can to existing practice risk assessments and say, what if we do the bare minimum to account for individual level differences? What then do we have to conclude about the group-wise labels and how they apply to individuals within the system? And so again, one of the main cons of this sort of approach is that we do have to specify sort of a functional form for that random effects distribution. We try two. One, we pick a normal distribution indexed by this parameter tau, which tells us how variable, or sort of, it's the variance parameter of a normal. So it tells us if it's large, we're learning that people are very variable about this sort of linear predictor, that xij beta. Essentially, that xij beta isn't telling us much. You have to know a lot about that individual to get a good estimate of their own, of what's going to happen. And if that tau is small, then we learn that those covariates are explaining most of variability. We also tried a discrete mixture distribution on the right. In practice, the results that we got were really similar across the two scenarios. So I'm going to only show you the results for the normal distribution because it's easy to talk about the tau rather than the discrete mixture. But if anybody's interested, I think I have some extra slides that will show you the results under the discrete mixture, and I can refer you to the paper where those appear in an appendix. All right, so the data that we have here is extensive data from the Kentucky criminal justice system. This covered June 2014 to December 2018. We reserved the last year, 2018, as a holdout. So training data was about 532,000 people, or arrests, not people, I'm sorry. And the holdout was about 79,000. So the covariates that we use, those things that go into X, are whether the current charge is for domestic violence, whether they're on probation at the time of arrest, whether the current charge is for a violent offense, some age-based things, if they currently have any pending cases, any prior misdemeanor arrests, number of prior felony arrests, number of prior FTAs, prior incarcerations, and if the current arrest is for an FTA. And these set of covariates are a superset of what is used in one of the most popular models. It's used to make FTA predictions. And the outcome is any FTA during the pretrial period. And if anyone has any questions about that, I'd be happy to answer that later, because I think that outcome variable is a little bit funky. Other information we have in this data set is the risk groups that were assigned by the other model that was used at the time of arrest. So when all of these people were arrested, another model, an actual risk assessment model, was used to lump them into risk groups. And so we have which risk group they were actually binned into by the existing model. I want to take a moment to talk about the shortcomings of this data set, even though it's honestly really great to have such a large data set to be doing this sort of analysis in. There are some things that I think are shortcomings in this case. So one, there are people for whom we don't observe an outcome. Those are the people who were not released. So standard practice and risk assessment is to drop those people. And so we follow that same standard. Again, the idea here is we want to sort of make the minimal change between standard practice and what we're doing here to see, again, if we just do the bare minimum to account for that individual level heterogeneity, how do our conclusions change? However, this does bias the data set, right? So if there are some people, for example, who are very, very likely to say fail to appear, and for that reason, they are not released and those are excluded. The other reason is that we could try to do some sort of correction, maybe some propensity score weighting or something like that. In order to believe that that is going to work, you would have to believe that we have all of the covariates here that would explain why someone would or would not be released. Of course, when standing in front of a judge, the judge has in some ways more information. They can talk to the person than what is captured by a few covariates. And so I don't think that's really justified anyway. And so we'd kind of rather leave it to the reader or the listener in this case to, assume or infer how they think that sort of data bias will skew the results. I see there's something in the Q&A. Did you want me to stop or shall I keep going?
I saw a question in the Q&A, so maybe so the question is that can you talk a bit about the number of observations that may be related to the outcome, and while repeated observation would be an indicator of recidivism and not necessarily FTA. If those may be related, are there concerns that the prior is being relied on more for a potentially different type of individual than those whom there are multiple observations.
Right. So can we talk about the number of observations? I can come back to this at the end. So yes, this is something that we thought about. One thing to think about in this case is that the number of observations has something to do more with the frequency than sort of the number of times person has been arrested total. So for example, someone could only appear in our data set once, but they could have been arrested 20 times before the sort of period starts. And maybe that first time that they appear in the data set, they remain incarcerated for the rest of the duration. And so we don't get to see them again. And so we did some sort of basic EDA to see how much we thought that that there were issues with sort of differences by occasion. And we concluded that it wasn't likely to be a huge issue, but it is something we'd like to look into in the future. I hope that answers the question. And if not, we can come back to it at the end. All right. Okay, and so like I said, in this data set, we do have multiple observations per person. So this shows the number of observations or number of releases we actually have per person. You can see most people we only get to observe once. Many people we get to observe twice, some 3 times, some 4 times, some 5 times, some 6, 7, 8, and up to I think 16, though not very many. And we did some initial simulation studies to figure out whether we thought this sort of distribution of number of observations per person was sufficient to get reasonable estimates of, say, tau in our model. And we do think that that is true. All right, so let me go through some of the results here. First, let me talk about model level results. And this is essentially those sort of global parameters get applied to everybody. So the betas and the tau, and in particular the tau, because that is the thing that is really driving how variable we think people are about those sort of their linear predictors, essentially. And so on the left, we see our posterior distribution of tau, and it's really pretty tightly clustered between 0.43 and 0.47. And so one of the analyses I wanted to do was think about how much of the variability in our estimate or in our distribution, our posterior distribution for P, came from 2 different sources. So one, the natural variability in P, that's sort of the expected variance of P if we know what beta and tau are. So once we fix those parameters, so how much does P vary once we know what the parameters specifically are, plus the second term, variability due to parameter uncertainty. So how much of that variance can we decompose and attribute to just not knowing what tau is? And the idea here is that I think it's a much more compelling argument if we do find that people are very variable and these group level labels aren't especially revealing about any individual. I think that's a much more revealing result here if it's the case that that's because we can estimate with high level of certainty that people vary greatly about their linear predictor, as opposed to having to say that we have a lot of posterior uncertainty about P because we can't nail down those global parameters, for example. And so one way to assess that is to look at the posterior distribution of P, averaging or sort of marginalizing over our posterior distributions of beta and tau. That is what is shown in, I believe, blue. The faces of people in the call are covering my labels there. So one is blue and one is black. And the other one is showing when we hold those 2 parameters fixed. So the beta and the tau parameters fixed. And we see that there really is no difference at all. So this sort of second term here is not contributing a whole lot to the sum. And so the variability in P is really a function of this natural variability that we're estimating. And we have high certainty about that. All right, so now I want to talk about results at the group level. So what do we conclude when we look at how these sort of grouping variables, like I talked about in the beginning, these sort of group level probabilities? And so one thing is that there are a few different ways we could think about grouping people. We could use those groups that were actually assigned to people, those group labels that were assigned to people when they were arrested and processed through the system. And that is what I'm showing in red up here. Those are called PSA risk groups, just based on the tool that was used to classify people at the time. Another thing we could do is bin our posterior predictive point estimates conditional on all previous observations. So suppose we observe you on your 3rd time, use the first 2 to come up with a posterior predictive for the 3rd, and then bin those. And we bin them so that we have the same number of observations or the same proportion within each of the risk groups as actually happened in the real world. And the 3rd version of this would be, again, using those posterior predictive distributions based only on all of the previous observations. running k-means, and so essentially not making the group sizes be exactly the same. I'm going to focus mostly on what happens if we think about this from the point of view of the risk labels that actually were used in the real world, but you'll see in all of the following slides, 3 figures, one like left to right. And so I'm going to be talking about the one on the left, which is in a red square, but the other 2 correspond to these 2 other cases. In general, they don't look tremendously different, so I'm not going to go too much into those differences. All right. So as I talked about, one of the ways that people have talked about, using the data in the case where you only say have 1 observation per person is to assume that everybody within the group has the same rate and then make sure that those groups are essentially calibrated. So in this case, that's what I'm doing. When I look at this PSA risk group variable, here I see the rate within each group is 0.08. Our estimate is 0.1. That seems pretty reasonable. And I have confidence intervals about that rate, just sort of the standard intervals about a binomial. Another thing you would notice here is that those confidence intervals do not overlap across those groups, with the exception of groups 5 and 6. So this sort of validation analysis this is like very sort of typical validation analysis that would say that, okay, the groups are different. Essentially, the averages across the groups are different. And in practice, how that would be interpreted would be that the people within the groups are different. The people in group 1 are different than the people in group 2 are different than the people in group 3, et cetera, et cetera. But people in group 5 and 6 maybe are not actually different. Maybe that should be collapsed into one group. All right. We could also look at something like this, which will take a moment for me to explain. So the black distribution here is our posterior distribution of P under our model for each of the groups. So this is just saying, how variable do we think that those individual level probabilities, or what's our posterior distribution for the pooled across all the people within that group of the distribution of those PIJs. The gray distribution here is essentially the distribution of the P hat IJs, which is that posterior predictive distribution using everything up until that observation. And so what we can see is that, at least according to our analysis, which is again the minimal change from what you would normally do to account for individual level variability, we see that people are highly variable within their groups. So we conclude that what's happening in reality is a lot more like the large variance scenario than the small variance scenario. People who are assigned risk group 6, for example, they have a reasonable probability, at least under our model, of having individual level probabilities that are much more similar to the stated probability for, say, group 1 or group 2 or group 3. There's substantial mass at the low end. Similarly for say group 3, we see there's a moderate amount of mass up near the top. And we can see these things look similar for the other ways of clustering or dividing people into groups. Another question we can ask once we have this full Bayesian model here is, what is our posterior probability that PI belongs to group G for each actual group assignment? So on the vertical axis here, we say if you are assigned to group 1, 2, 3, 4, 5, 6, what is our posterior probability that you actually belong to groups on the horizontal axis 1, 2, 3, 4, 5, 6? And so this is essentially a heat map. So a brighter blue color means a higher probability, and a more white or purple value means a lower probability. So essentially we're saying, what is the posterior probability that your PIJ falls within each of the ranges of the bins where the cutoffs are picked to be the midpoint between the rates for each of the groups. And so we can ask something like, what is our posterior probability that we got the group, quote, correct? And so for the PSA risk group on the far left, we'd estimate that to be about 25%, which may seem a little bit surprising, but keep in mind that most of the people are not in any of the extreme groups. And so we end up saying, okay, there's actually not that, the probability we get it right is actually fairly low, just due to this sort of overwhelming level of variability within the groups. I think once we have these full posteriors, we can ask some new and different questions that we aren't really able to ask when we don't have a model that accounts for individual level variability. So one thing we can look at is to try some different strategies for dividing people up, maybe based on statistical confidence. So in this case, I've arranged each individual's confidence interval, or actually 10,000 randomly selected ones, because otherwise this is just a huge mess, And I've arranged those 95% posterior credible intervals for PI ordered by median. I kind of switch something in the middle so you can see what's going on. And I've colored to show two groups whose intervals do not overlap. So maybe instead of dividing people up by their point estimates, since now we know those point estimates we have a lot of uncertainty about those point estimates, right? Maybe we'd want to be able to divide people into two groups where we could say we have high certainty that the people within these groups are different, since this is how people tend to interpret these sorts of results. Anyway, they tend to want to say, okay, the people in this group are different from the people in this group because those group-wise confidence intervals, for example, don't overlap. So if we were to do an exercise like this, we'd find that we could really only flag, I think it's 5 to 7% of people as being in one of the upper or lower groups, the groups that are actually sort of statistically really distinct from one another. And so given that the point of doing this whole exercise is to divide people into groups, if we can't really, and we'd have to save for all the people in the middle, all the gray folks in the middle there, we just can't know. We don't really know if they're more similar to the high risk or the low risk end. This maybe seems like not the greatest idea here. Another way that we could approach this, and I think this is actually a new way of thinking about, I don't know, fairness, whatever, in this area, is to think about the following. You could say, maybe we only want to flag people whose individual probability is greater than C, and we have certainty H about that. So there's sort of two probabilities going on here. That gets a little bit confusing. So our posterior probability that their individual level probability exceeds C is at least H. So we show that here for various values of H, our certainty, and C, that threshold. And we see here that depending on what we pick for C and H, we can flag various proportions of the population. So if we set C extremely low, the marginal rate within this data is about 20%, so about 0.2. Then we can flag a lot of people. But if we start making, sort of standard demands, like maybe at 95% certainty, that's that H equals 0.95, and say we want to be more certain than not this person is going to fail to appear, well, we can't really flag, maybe we flag a couple people, but not very many. It's a very, very small percent. And we really have to go pretty far down that threshold. So down to maybe, I don't know, 0.2. So that would be the median. Are they greater than the median or not? And we can still only flag about 10% in that case. Or we have to really relax the notion of certainty that we care about. So we could have H equals 0.75 and C equals 0.2, and maybe we could flag a quarter of people more or less as the higher risk sorts of people about whom we have, an acceptable level of certainty that their individual probability is high. And I kind of like this approach in some sense because it's consistent with the value that we should wait for enough evidence to accrue about the individual before flagging them and not just rely on their noisy point estimate by itself. So the final thing I want to show you is essentially the thing on the right. The image on the left, I think, is less useful in this case. And so what I want to convince you of is that the results of this analysis, essentially that people within groups are highly variable. The group labels are not essentially meaningful descriptors of individuals. That was not a foregone conclusion of our model setup or of this analysis. So the red line here shows the interval length, or our 95% interval length, as a function of the number of times we'd have to observe an individual, and for the tau that we estimated in our data. So red is for the tau we estimated in our data. And we see that we would, I believe, have to observe an individual. Sorry, I put this on the log scale, so it's a little, you got to kind of wrap your head around it a little bit funny, but we'd have to observe a person about 100 times to get that interval to a length of about 0.1. So to be able to say that, say, someone's probability is about 0.1 to 0.2, we'd have to observe them 100 times because we estimate tau to be fairly large in this case. And we're very certain about that, about how large that is. In practice, that's not going to happen. Like 100 times is a lot. However, if the data had led us to believe, or if we had estimated from the data that tau was in fact much smaller, which you see in the dotted line and the dashed line, then we could have much fewer observations per person, and we could actually say with confidence. So that say the interval was about 0.1 with many fewer observations. I think even one in some cases in the minimal example. And so the point here that I'm trying to make, again, is that the model setup didn't lead us to this conclusion. It was the data. There were opportunities for the data to tell us otherwise. The data could have told us that people did not vary within their groups. What happened is that the data told us that essentially there is not very much signal in those covariates. Individuals vary very widely about those. And so I'm going to start winding down here. There are, of course, some limitations to this type of analysis. And one of those is that the random effects distribution family, we did have to pick that. I've talked mostly about the normal. The results were qualitatively similar using a more relaxed one, a sort of a discrete mixture one. And so that gives us confidence that this is not something that is, just coming from that prior distribution. Of course, we have the linear model structure. Predictive performance does not seem to vary too much based on which covariates are used or different types of model flexibility, at least preliminarily, not with including the individual level stuff. We did, some EDA or we fit a variety of models, and throwing more complicated model structures at this did not seem to change dramatically anything about predictive performance. And of course, the random effects are constant across time, no individually varying regression coefficients, et cetera. And I'd point out here that the additional complexity that we could add by changing those things by, say, adding time varying random effects or individual varying regression coefficients would only likely increase our posterior uncertainty. So to the extent that we've already concluded that by making this minimal change, we don't know much about individuals within groups, if we were to relax the sort of rigidity of our model even further, I think we would only come to that conclusion more strongly. So I will definitely wind down here by saying that these RAIs, these risk assessment instruments, are used to assign these labels, medium, high, low risk, to real human beings. And those labels affect the trajectory of their lives. I gave some examples in the beginning. It can affect outcomes of court cases. It can affect their personal situations, jobs, etc. So after doing the minimal thing to account for individual level variability that's not accounted for by covariates, we find there's considerable between individual variability that swamps the little signal there is in the data. So we find that the labels that are assigned to people aren't especially meaningful representations of their individual level probabilities of the outcome they purport to explain. We also find we'd have to release people an unrealistic number of times before we could have small enough intervals to give, given the covariates that are currently available. Now, of course, again, we have to give the caveat here, given the covariates currently available, if there were other covariates that were massively more predictive or explanatory, perhaps that conclusion would change. And again, sort of to really drive home the conclusion here is that the groupings may be useful at the aggregate level. So from that policy level of doing planning about how many people might fail if you were to use this as a rule for release, but they offer little information about individuals. So if you're the person who's being evaluated or the judge who's having to make a decision about an individual, that offers little information. So that concludes, I think, right around the time I'd hoped. And I'm very happy to stay and answer questions for anybody who has them.
Great. Any questions for the speaker?
I saw some in the chat.
Oh yeah, I saw a question in the. Yeah.
Oh no.
Yeah, that's a question from the Q&A section. So, would RAIs be used to make release decisions in the Kentucky data?
Yes, so they're being used to inform release decisions, and that is one of the things that I think is sort of one of the things that people often say these aren't the tools that are making the decisions, they're informing decisions. But yes, they were informing decisions. And in fact, so a lot of this analysis, when I was saying the grouping variables that we used that were used in reality, those were based on a tool that was used within this data, that was used that created this data, however you want me to say it. It was used at the time this data was collected. Maybe that's a better way to put it.
So here's another question. Yeah. Do you want me to read? Oh, maybe I will read it to the audience because I think some audience may not be able to see the questions. Okay, so the question is, how do interpretable models compare to non-interpretable models like random forest in the quality of their predictions?
So there are mixed opinions about this. I think that, one thing you need to understand about doing these sorts of models is that you're kind of constrained in the sort of information you can collect. You can do the interview questions and get a lot more covariates, but you also are often limited to what's collected in the criminal justice system. And so that data can be really rich in the sense that there's, text data, there's all this sorts of things, but it often gets condensed to things like simple counts, and there aren't a whole lot of those. And so what I've seen trying to apply things like random forest is that the predictive difference really, they don't perform incredibly differently. There are some other folks who have come to different conclusions, and actually I'm working on a project right now to kind of work out why and when that may be. But in my experience, and I've looked at a lot of these sorts of data sets, it doesn't seem to make a huge difference one way or the other. The sort of linear, I mean, and you kind of think about it, right? Most of those covariates are categorical. There aren't a whole lot of categories. You could throw in some interactions, and essentially if you throw in all the interactions, you're not going to get anything better than that anyway. And so that's, yeah, the answer is that I don't personally think it makes a whole lot of difference, but you'll find people that do.
Okay, so the next question is that, do you try doing the analysis including the race variable? If so, what happened? And if not, why not?
Okay, so in this case, we did not throw in the race variable, and there are a variety of reasons for that. So I think the most important reason that we didn't do that is essentially legal constraints. Like if you were to we wanted to build a model that is similar to something that could be used in practice, and again, is sort of the minimal deviation from what's done in practice. In practice, I believe for legal reasons, you can't actually include a race variable directly into a model. And so we didn't do it. It is really popular these days to look at results disaggregated by race, which is essentially that whole thing about fairness, right? Does the model performance similar, disaggregated by race? We do have race information in this data. So I think that's something that's really important to look into. I kind of ascribe to the idea that each paper should have like one main idea and like one main thought. And so in this case, we weren't specifically focused on the issue of race, but sort of this broader issue of incorporating different ideas of statistical uncertainty and what they might mean about fairness. Like in this sort of, fairness has come to mean a lot of things. It often means this sort of disparity-based notion of fairness, this idea that different people, like different groups of individuals, have different model performance. That would be sort of unfairness. I think there's also what I would call like the sort of playground version of fairness, like, hey, that's not fair. And I think that's kind of what our statistical uncertainty notion is really getting at, saying like, hey, it's really not fair to detain somebody if you can't be sure that their probability is actually high. And so we are sort of trying to flip it around a little bit and come at it from a slightly different angle. But of course, and especially in the context of this lecture, racial disparities are of the utmost importance and have gotten a lot of attention over the last several years in this area.
Okay, thanks. So another question is that for the individuals that have only one observation, are their theta I going to be the same? Or in another way, if I have two people and they have the same covariate, but they both only have one observation. So in this case, will their posterior probability of FTA differ?
So, okay, if their covariates are the same and they have the same outcome on that one event, then yes, their posterior distributions for theta I will be the same. But as things change over time, for example, as we say, observe them on more occasions and their theta I's are different on those different occasions, or their outcomes are different, they will of course diverge. But that's a great question. Yes, on the first time we observe somebody, if they have the exact same covariates and the exact same outcome, then yes, our posterior distributions would be the same.
Okay, thanks. So the next question is that, have you spoken with the policymakers or other stakeholders about your research finding? If so, and what are your experience being like in this case? And are the non-statisticians open to different approach, and then what is typically used for these risk assessment methods?
Yeah, this was actually really a project that was kind of a joy to work on, because I was working really closely with people who actually work with these models on a day-to-day basis. I will say that, and I think you can probably infer that from my tone, I'm fairly skeptical of these sorts of models. And I think there are other issues as well, like the outcome variable is a little bit funky, like did you ever fail to appear? So if you had 100 court dates and you appeared for 99 of them, and you failed for one, that counts the same as if you had one and failed for one, which seems a little weird to me. There are a lot of reasons why I feel like I understand where people are coming from with wanting to apply models in this case, but I think the stakes are too high and the signal too low that you can meaningfully say things about people. This is basically where I've landed on this. That said, I understand, why people want to do it. And so this was an opportunity to work with folks who actually are really in the weeds and working with people and using these models day to day. So we did actually talk to them about our approach. They had a lot of really great feedback about the data. And essentially, I think they were, I don't know if surprised, I don't know, disheartened. I think this is something that people who have real life experience kind of know. I think it's something that if you've dealt with people or you're sort of in the thick of it, you do understand that there are some people who are probably really going to show up based on information that's not included in the model, and some people who aren't. And so this is something that people who work in this area in non-quantitative ways, I think, have been saying for a long time. And so I think part of this project was to, one, see if that was borne out in the data, and two, if so, be able to give some sort of quantitative justification to those arguments. Because what I've found working in this area, in many areas, right, is that numbers really talk. And so you can have, people with real world experience, with incarcerated people, with, people who are criminal justice involved, saying these sorts of things, and they can say it till they're blue in the face. But when you have something that has sort of like the, gravity or like statistics and numbers really have a power, that people think it's more objective, or there's, there's something more believable about them. And so I think being able to offer some sort of statistical backing to other interpretations of data or other interpretations of what's going on, I think is an important role. And so I kind of veered off that question a little bit. I found people to be interested, I'd say, in this project and various other projects in this area. And of course, I mean, that there, no group of people is a monolith. Some people have really dug their heels in, built their careers around building these sorts of models, and the models can do no wrong. Essentially, it's just being irrational to think there's anything wrong with doing this. There are people on the other end who think that, any kind of modeling of a human or prediction about a human is sort of fundamentally maybe inhumane. And so people vary. I guess that's what I can say. I feel like I've had fairly good luck talking to people about these things, though, and having a receptive audience.
Great. So the next question is that, can you discuss that about like the many different fairness metrics that exist out there beyond the two that you have discussed? And like, are there any fairness metrics that you prefer over the others? And are there ways you think that these metrics can be improved?
Yeah, I think, yeah, sure. Okay, so we've talked about group fairness, obviously the sort of disparities in predictive performance. We've talked about individual fairness, or sort of metric fairness, where you have, people who are similar by some notion of similarity should be treated similarly by the model. I'd say the other main branch of this is causal fairness, where people write down causal models of the world and define causal pathways that are acceptable and others that are not sort of morally acceptable, and then try to ensure that their model only uses the pathways that are morally acceptable causal pathways, and sort of doesn't correlate or doesn't inherit any of the characteristics from the unacceptable pathways. I think those are probably the biggest three in the algorithmic fairness literature. In terms of what do I prefer, I think of all of these sorts of metrics as not the final word, but evidence one way or another. I think, in circa 2016, 2017, maybe even before that, honestly, maybe 2013, there were some early papers on this, in particular by like Moritz Hart on, building models with the same false positive rates across different groups. There was like a lot of excitement about creating models by, say, adjusting your loss function so that you could, meet some notion of fairness, largely the group ones. I think over time, as this field has matured and come to appreciate a little bit more nuance, I don't really think the right solution is probably ever going to be like, let's just define like that it's always okay, equal false positive rates, and it's that simple. I think understanding fairness is going to have a lot more to do with understanding the context, thinking through what the impacts of such a model will be. It's become, of course, I think all of us are aware that racial disparities in the criminal justice system are large, and in my opinion, are a huge problem. And I think a lot of people are pinning their hopes on these sorts of models to do something about that. And so far, we haven't really seen that. So I think it sort of comes down to like the impacts. rather than just sort of saying, okay, if the model, meets some fairness criteria, then we're all good to go. I think that's honestly kind of like the easy way out. And I think the hard way out is doing the ongoing evaluation, seeing how it's interacting with human decision makers, seeing how it's interacting. Like, look, this is only one decision point in a complex process, right? Like there's the whole policing issue on the front end, which is how people end up being evaluated by one of these models in the first place. So conditioning on all of that and making a claim about fairness is sort of implicitly saying all of that stuff up front is fair, which is a huge problem as well. And so I guess what I'm saying is, do I have a favorite? No, it's kind of hard to pick your favorite child, I guess. But I think all my children are maybe imperfect, and it requires a whole lot of different ways of thinking about the data, and thinking about the process and the system, and doing ongoing work to make sure that the introduction of a model is having the impact that will lead to a more fair or just society.
Great. And so the next question is related to the previous question. Like, have you tried to communicate this result to legal or policy people? And how do they respond to the concept, like the probability of a probability?
Yeah.
And also on the potential issues along these lines.
Yeah, that's even hard for me to wrap my head around. Like, it's sometimes you kind of start talking and you get tongue-tied because you're like, wait, the probability? No, I mean, honestly, I think I've had pretty good luck. And again, I'd say, results are mixed. Your mileage may vary. I've been in meetings where I've said, for example, why are you showing just the risk group, high, medium, low? Why don't you at least show the average rate within the group? And I've been told that judges can't understand proportions, which I found confusing or percents, like I assume they understand sales or basic things like that. So that seems kind of weird that they couldn't understand a percent, but I've been told that on one hand. I've also worked with this really awesome, or at least presented to a really awesome group of civil rights attorneys who really grokked this. They're really into it and wanted to incorporate it into how they talk about things. And so, yeah, I think that's always a challenge. I mean, honestly, even for statisticians, it's a challenge. Like thinking about what a probability is, that's really kind of a philosophical foundational question. It gets really hard. That's one of the reasons I prefer this sort of Bayesian approach, because it's at least sort of, I don't know, straightforward or maybe coherent way to think about things. Yeah, no, man, that's a problem. It is, especially when you get that sort of wide variety of backgrounds and statistics and quantitative comfort, I guess I would say.
Great. So the last question. So are you aware of any other AI tools for other aspects of the society? For instance, it's well known that the social workers are generally highly overworked, especially when it comes to dealing with like a child welfare. So I would think that AI tool may at least help them to gain some, organization help into their case. So what are your thoughts?
Yeah, I mean, I think these sorts of tools are used all over the place. I think, the sort of details of them vary. So this question asker is exactly right. Another, I don't know if I would say popular, but popular in the algorithmic fairness literature genre is the sort of child welfare area. Of course, there are medical tools that help physicians understand the risk for patients. There's any number of ways. I mean, risk assessment as a sort of idea is, far reaching, right? You can do risk assessment of bridges. You could do risk assessment of really any sort of action. And so the ones that I'm thinking about, like you said, the criminal justice, the child welfare, medical are the ones that I've heard about the most, but I wouldn't be surprised if there are these sorts of point-based systems or sort of more structured and quantitative versions of this floating around for any number of application areas.
Great. Yeah, a lot of very exciting questions. And any other questions for our speakers?
Thank you, Yates. I see your comment.
Yeah, it's a great talk. It's amazing. It's really amazing talk. Yeah. So if we saw other questions, so then let's thank the speaker again for this really wonderful talk. And thank you so much for this really interesting work.
Awesome. Thank you so much for having me. Like I said, it's really an honor to get to talk to you all, and I hope that was useful or enjoyable.
Yeah, thanks. And everyone have a nice weekend.
Bye.
Bye. Thanks. Thank you. Oops.